Hello everyone, hope you are doing well. I'm Reza, founder of the optimizationcity.com. In this film, we are doing some exercise for transportation problem in operation research. So let's move on.
Let's note that it's a very important point we should consider. It's important to highlight that the optimal solution in this table remain unchanged from the initial case that we don't have the production cost and selling price. And the case involving a production case, which is the last with a different cost. The addition of the fixed value to the cost in the column or row does not alter the optimal solution, which is very important. So let's solve an example in the transportation problem. A canning company operated factory in the three cities, Chicago, Cleveland, and Boston. During the previous week, the production output of this factory was also 35 units from Chicago, 50 units from the Cleveland, and 40 units from the Boston. Now, the company aimed to transport this product from to the four different distribution centers: Dallas, Atlanta, San Francisco, and Philadelphia. The desired quantity to be shipped are 45 units to Dallas, 20 to Atlanta, 30 to San Francisco, and another 30 units to Philadelphia. To determine the cost optimal shipping method, we consider the production and transportation cost between each factory to the distribution center. The table below illustrated this pattern. So we have the three factory in Cleveland, Chicago, and Boston, and the four distribution center, which are warehouse, Dallas, Atlanta, San Francisco, and Philadelphia. We have the supply and demand here. How we can solve this problem considering the all cost? So we start with the initial step. In the initial step, we find the initial basic feasible solution. We have the two methods. The first method, the northwest corner method. We start from the x11 and do the following process as we discussed in the course. So this is the initial basic solution for the northwest corner rule with the objective function 1180. So there is another way, Vogel approximation method we use here. As you remember, we calculate the column difference and we pick the column and row difference and we pick the maximum, and in the maximum we find the minimum value and the maximum value we can set from the demand and the supply. So here this is the 13 and we update 13 and 14. We have the 0 and we have the 10 and we add the row column 4 and we go forward to find the initial basic solution using the Vogel approximation method. So in this case, the optimal solution is 1020, which is less than the basic initial solution for uh, north corner way. After comparing the objective function obtained from the northeast corner rule and the Vogel approximation, it becomes evident that the Vogel approximation yields the better objective function for the basic solution. Consequently, the algorithm will adopt the initial solution derived from the Vogel approximation. There are, since in the stopping condition, we should calculate the reduced cost. Since there are no basic variable with the value of the Cij minus ui minus vj, we calculate as a follow. We just set ui as a u1 as a 0 and calculate the dual variable as a follow. So we have arrived the optimal solution because the all reduced costs are positive. This clearly demonstrates that the Vogel approximation method effectively guides us toward the optimal solution. For additional practice, let's consider this initial basic solution. So in the stopping condition, we assume u1 as a 0 and define the value of the dual variable as a follow. So this is the dual value for u and y and v. In the table here, we calculate the reduced cost. We observe that there are two non-basic variables where the Cij is less than 0. Uh, this indicates that the current basic solution is not optimal. So this is 2 minus. We need to seek and improve the solution. To accomplish this, we select x1, 3, and 3, 2. X1, 3 as the basic solution, as the entering basic variable. To accomplish this, we select x1, 3, and we process the identifying the output variable as a follow. So we just add the arc 1, 3 with the flow of theta. So if we add the theta to node number 3, we should decrease the flow from 2 to 3 by theta. And if we decrease the theta from node 2 to hold the balance condition, we should add the theta to arc to 1 and go forward. This is the cyclist process, and we can find the theta is the maximum value of theta is equal to 15, and this is the basic solution. X11 is replaced by the non-basic variable x13 in the base. So this is the new basic solution. So in the stopping condition, we set u1 as a 0, and the value of the dual variable can be calculated as follows. In the following table, you can see that the reduced cost for all non-basic variable, and we have the one negative value. So we add the arc2 to the basic variable, and we do the cyclist process. The maximum value of theta would be equal to 10. So this is the new basic solution. In order to check we reach the optimal solution, we set u1 as a 0, and if we calculate the dual value of the all our nodes, so this is the reduced cost, and we can see that all reduced costs are non-negative, so we reach the optimal solution, and this is the optimal solution of the transportation cost. Thank you so much for watching me. If you are any question and need any assistance, please do not hesitate to contact us by email or by form or filling the contact form in our website, which is www.optimizationcity.com. Thank you so much, and goodbye for now.